Yeah. Good evening, dear participants, and welcome back to session 4. It's really a warm, it's a warm welcome to Dr. Venkateswara Rao Kagita, Assistant Professor. He's an Assistant Professor from NIT Warangal, and who is our distinguished speaker for the session 4 of this ATAL FDP on the title Foundations and Applications of Data Science. He will be delivering the session on supervised learning, regression and classification model. Dr. Venkateswara Rao is an assistant professor in NIT Warangal. He has earned his PhD degree from University of Hyderabad, and he's enriched his global academic experience as a visiting fellow at the University of New South Wales, Sydney. His research focus is on the areas data mining, machine learning, and deep learning, with a special emphasis on building advanced techniques for recommender systems. He has successfully secured 7 research and consultancy projects worth over 2.85 crores, funded by the premier Government of India agencies. Dr. Venkateswara Rao has published widely in top-tier journals and reputed international conferences. Beyond research, he is a sought-after speaker, having delivered expert talks at leading institutions, including NIT, IIT, and other universities in India and abroad. Welcome, sir. Hello.
Thank you very much, ma'am.
Yeah, welcome, sir. Welcome, sir. Welcome for today's session. Yeah, thank you.
Thank you. Shall I begin?
Yes, sir.
Just give me a second. I'll start. Sorry for that. Let me share my screen and I'll start. Is it visible?
Yes, sir. The meet is visible, not the presentation.
What about now? Is it visible? The presentation?
Yes, sir. Yeah, supervised learning. Yes, sir.
Yeah, all right. Hello, everyone. Very good evening. So I was asked to cover the supervised learning, which includes regression and classification. Let me see to what extent I can cover in 1.5 hours. But I'll start with the supervised learning, different types of problems in the supervised learning. So only one thing that I expect from you is that please make this session responsive. In a sense, like if I ask some questions, please do respond. And if you have any questions, please feel free to interrupt any point of time and ask any kind of questions that you have. So you can unmute yourself at any point of time and ask any kind of questions that you have. Okay, that way you can make this session interactive. Don't type it in the chat box because I can't see it when I'm in the full screen mode. All right, so if I ask something, please do respond to me. Okay, all right, so let us start with the supervised learning. But before that, let us also try to understand what is the difference between classic versus the machine learning approaches. And then we'll also have a quick look at different types of machine learning algorithms. Then we will start with the supervised learning. We'll deep dive into the supervised learning. All right. So what is the difference between the classic versus the machine learning approaches? All right. So in case of the classic approaches, to distinguish between the classic and the machine learning approaches, I have taken a couple of examples. Let's go through them. Then you'll get an idea of the difference between the classic versus the machine learning approaches. So here is one of the examples I have taken, classification of the swan versus the duck. Okay, so here is a classic approach. In case of the classic approach, what we are doing is that we're defining some explicit rule, something like this. If the neck length is larger, then it is a swan, otherwise it is a duck. All right, that's what the basically classic approaches does. They assume that we have the domain knowledge, and that is explicitly defined as a rule in terms of a rule in a program. All right, that's what the classic approaches does. On the other hand, what machine learning algorithm does is that they supplement the mission or the algorithm with a lot of examples. Like for example, here a lot of images of the swans and the ducks are given, and from the images we extract the neck length and represent each image with its neck length and the corresponding class indicating whether it is a swan or a duck. So given these examples, the machine learns a pattern. The algorithm, machine learning algorithm learns a pattern automatically, and it determines this rule from the given data. It means you need not have to explicitly define this rule. The machine learning algorithm itself learns this rule from the given data. So that's the difference between classic versus the machine learning approaches. So to make you understand even more better, I have one more example here, which is the house price prediction. So let's say we want to predict the price of a house based on various characteristics of a house. So various characteristics includes size of the house, size of the garden, number of rooms it has, right? So what classic approaches does is that they assume that house pricing formula is known to us and it is explicitly coded. So something like this. So price is equivalent to 1.2 times of the size of the house plus 0.7 times of the size of the garden plus 3.1 times of the number of rooms it has. All right. So we assume that, the algorithm assumes that we know this formula and it is explicitly coded. All right. So suppose I have given a data something like this. For the sake of simplicity, I'm only considering one feature, which is the size of the house. And let the data given to us is something like this. If the size is 100 square yards, the corresponding price is 300. If the size is 200, the corresponding price is 500. Size is 300, the corresponding price is 700. And it is 400, then the corresponding price is 900. So we have given this data and we ask a question of how much can we expect if we have the house with the size of 500 square yards. All right. So this is the question that we are asking. So can you see any pattern in the given data? And according to the pattern that you can see, can you tell me what would be the price? Anybody? Speak up.
Sir, the screen is not visible.
1100.
1100, sir.
Yeah. Oh, is my screen visible, by the way?
It's visible, sir.
Yeah, it is visible.
Sir, please check. Maybe.
Mr. Praveen, can you rejoin?
Yeah, I will rejoin. Okay.
All right, it's 1100, right? How did we get this 1100?
1100.
Yeah, it's 1100. Yeah. So how did we get this 1100? We analyzed the data and we found some pattern in the data, right? And the pattern that we found is this. The price is equivalent to 2 times the size of the house plus 100. So this is what the pattern that we found from the given data, right? And we make use of this pattern to make a prediction for the future instances. So given any new instance for which we know the size, we just substitute the size in this formula and we get the corresponding price, right? That means we're just supplementing the data with supplementing the machine learning algorithm with the data, and the machine learning algorithm is extracting a pattern. We also call this pattern as a model. We also call it as a hypothesis. We also call it as a model. So the algorithm learns the model from the given data, and we make use of that model or the hypothesis to make a prediction for the future instances. So that's the beauty of the machine learning algorithm. That means you need not have to explicitly define a rule, something like this, as in case of the classic approaches. They have the ability to automatically extract the pattern from the given data. That's the beauty of the machine learning algorithms. So that means they model the relation with some unknown variables, ABC, and they determine this ABC from the given data, right? That means whichever ABC is able to estimate the prices correctly, we choose that ABC. So how to choose? It's a part of learning, and we're going to see it as we proceed. All right. So there are different types of machine learning algorithms. They're broadly classified into 3 types: supervised, unsupervised, and reinforcement learning. In the supervised learning, we have regression and classification problems. In the unsupervised, we have clustering and dimensionality direction. And various applications of supervised learning includes medical diagnosis, farm filtering, etc. Unsupervised, targeted marketing, customer segmentation, image color compression, and there are many more. Reinforcement learning mainly used in game AI and some real-time decision making, skill acquisition, self-driving cabs, etc. Robo navigation also. All right. So the main focus of this lecture is on the supervised learning. I'm not focusing on the details of these different types of machine learning algorithm also, because I'm assuming that it might have been already covered in one of the previous lectures. Right. So the main focus of this lecture is on this supervised learning. We'll be targeting both regression and classification, but let's see to what extent we can cover. I'll start with the regression problem. Right. So, but before that, let us try to understand what is supervised learning. So in the supervised learning, the data is labeled. That means for every instance given to us, there is also a label associated with it. And here, the label is acting like a supervisor to guide the learning process. That means when the machine learning algorithm comes up with some kind of prediction, to judge whether that prediction is right or wrong, we have the ground truth available with us. And that ground truth or the label is acting like a supervisor to guide the learning process in a way that it adjusts the model so that it will make correct predictions in future, right? So that way, the label is acting like a supervisor to guide the learning process. So that is why it is called supervised learning, because the label is acting like a supervisor to guide the learning process. So depending on the target variable type, we have 2 problems, regression and classification, that we will see. But let us try to understand what do we mean by the label data in detail. So here is an example of the label data in which we have given images and the corresponding labels indicating gender of an image. So this is an image and the corresponding label indicating the gender, such as a female image. Similarly, male, male here, and so forth, right? So we have given this data, and we have also given a new instance for which we only have the image, but we don't know what is its label. The task is to make a prediction of this new instance, right? The label of the new instance. So this is how a typical supervised learning problem looks like. All right. So for any domain of interest, one could extract these features and represent the given objects or the images in numerical format, right? So for example, given this image, one could extract the features like height, waist length, eyebrow width, hair length, leg length, eye width, and so forth, right? So for the sake of simplicity, I'm only considering 2 features and representing each image on the 2-dimensional space. So we call these features as the input variables. So here, I just represent the image, each image with the 2 features or the attributes, height and the waist length. We call them as input variables. We call them as input variables. And the corresponding label, we call it as an output variable. That means for every instance, we have given input variables and the corresponding target variable. Input variables and the corresponding target variable. Okay, and for a new instance, we only know the input variables, but we don't know what is the corresponding target variable. That means if I try to formulate a supervised learning problem, I have given the input variables x1, y1, x2, y2, and so on, xm, ym. All right, where xi is the input variable, vector of input variable, the dimensional feature vector we call it as, and yi is the corresponding target variable. Okay, yi is the corresponding target variable. All right, so given this data, we have also given a new instance xm plus 1, for which we only know the input variables, but we don't know what is the corresponding target variable. The task is to make a prediction for that. So this is how a typical supervised learning problem looks like. All right. So now I said that there are two different problems in the supervised learning, and that depends on the target variable type. If the target variable type is discrete, that means if the output variable type is discrete, if this is discrete, we call the problem as classification problem. If this is continuous, we call the problem as regression problem. Okay, if the target variable type is discrete, we call the problem as classification problem. And if the target variable type is continuous, we call the problem as regression problem. So what do we mean by the discrete type? Discrete type means it takes finite and countable number of values. And if I take any two continuous values, it's not possible to get another value which is in between them. Then we call that kind of variables as discrete variable. Like for example, if I throw a 6-face dice, what are the possible outcomes? I can get either 1 or 2 or 3, 4, 5 or 6. Is it possible to get 1.5? Or is it possible to get 2.3? Anything like that, which is in between two continuous variables, two consecutive variables, two consecutive values. Is it possible to get? Hello? If I say, if I throw a 6-face die, is it possible to get 1.5 or 2.3 or anything like that?
No, sir.
Not possible, right? Right. That means if I take any two consecutive values, it's not possible to get another value which is in between them. We call this type of variables as discrete type. And if you are interested in making a prediction for the discrete type, we call the problem as classification problem. That means you're trying to classify the new instance into one of the k classes, right? If k equal to 2, we call it as a binary classification problem. If k is more than 2, we call the problem as multi-class classification problem. Multi-class classification problem. When k greater than 2, we call it as multi-class classification problem. So can you tell me whether this example is an example of binary classification problem or multi-class classification problem? Is it a binary classification problem or multi-class classification problem? Everybody, please try to respond. Is it an example of binary classification problem or multi-class classification?
Binary classification.
It's a binary classification problem because there are only two classes, right? Male and female. Right. If it is more
Binary,
than 2, yeah, great. Thank you so much for responses. All right. So this we call it as a classification problem. All right. So instead, if the target variable type is continuous, we call the problem as regression problem. That means if the target variable takes any continuous value, any numerical value, we call the problem as regression problem, right? Let's suppose here the label indicates weight of a person instead of a gender of a person. So weight can take any value, right? There is no restriction for them to take certain values only, right? Weight can be 68, weight can be 69, weight can be 68.1, or weight can be 68.11, or weight can be 68.99. It can take any value. There is no restriction for them to take certain set of values only. So this kind of problem, we call it as a regression problem. The target variable type is discrete, we calling problem as classification problem. If it is continuous, it means if it can take any numerical value, we call the problem as regression problem. So I hope the difference is clear. So to understand it further, I have given few examples. Please help me to classify them as regression or classification. So I'm expecting responses from most of you, right? So please do respond. Email spam and non-spam filtering. Is it a regression problem or classification problem?
Classification.
It's a classification problem, right? Yeah. House price prediction. What about
Regression.
this? It's a regression problem. Detection of the news article type, whether it is a political news, cinema news, or crime news, etc.
Classification.
It's a classification, right? Yeah. What about the detection of the news article? Okay, all right. Marks prediction. That means how many marks a student would get.
Regression.
Or it's a regression, right? Yeah. What about the grade prediction?
Classification.
Regression.
It's a classification, right? Grade, A grade, B grade, C grade, D grade, etc. Right? One of the few grades. What about weather forecasting? Whether it is a sunny day, rainy day, cloudy day, what would be the tomorrow's day?
It's classification.
It's a classification. What about the temperature forecasting? What would be the temperature tomorrow?
Regression.
It's a regression problem. That's great, right? So as you've got sufficient understanding about the regression and the classification problems, let us try to explore each one of this one after the other. Mostly we'll start with regression and the similar approaches for the classification also. Once you understand the concept of learning, it is easy for you to make a connection to any other algorithm also. So let us see, start with the regression problem. But before that, let us have a quick look at a simple machine learning recipe for the supervised learning problems. A simple machine learning recipe for the supervised learning problems. Here is the recipe. The recipe is so simple. We have given a training data. So the training data is passed to the learning algorithm. Learning algorithm tunes the parameters and gives you a model. So once you get this model, you make use of this model to make a prediction for the future instances. So given a new instance, you're classifying it as a cat versus non-cat. All right. So here's the process. So you have given the training data, which is passed to the learning algorithm. Learning algorithm is giving you a model. Now you're making use of this model to make a prediction for the future instances. All right. So that's how you make a classification. I mean, that's how the recipe works for the supervised learning problems. All right. So this is the idea. So you have passed a lot of training examples to the model, and it tunes the model. Now during the testing, right, you are making use of the trained model to make a prediction. So given a new image, you're classifying it as a dog versus cat or anything like that. All right, it's a classification in this case. So this is the recipe, as I have told you already. So you have given the training set. The training set is passed to the learning algorithm. Learning algorithm gives you the hypothesis. We also call it as a model or a pattern. Now you're making use of this hypothesis to make a prediction for the future instances. So let us start with an example. So we'll start with the regression problem, as I have mentioned. Let's start with the regression problem and try to formulate the regression problem. So as I have mentioned to you, in any of the supervised learning problems, you have given x1, y1, x2, y2, and so on, xn, yn, where xi is the d-dimensional feature vector and yi is the corresponding target label. If the target variable is continuous, we call the problem as regression problem. If it is discrete, then it is classification problem. So here yi is the continuous target variable. Now we have also given a new instance xm plus I, for which we have to make a prediction of the corresponding target variable. So this is the problem. All right. I hope everybody got the problem. You understood the problem, right? In mathematical terms, the formulation is clear, right? What is the problem?
Yes, sir.
Is it understood? Yeah. All right. So let us start with an example. So how do we predict the housing prices? So we collect the data regarding the housing prices and we analyze how they related to the size in square feet. How they relate to the size in square feet. Here, for the sake of simplicity, I've only considered one input variable, which is size of the house in square feet. And the corresponding target variable is the price. So each cross mark here indicates one house, wherein we have two dimensions of it. One is the input variable and other one is the output variable. So we have given this data. Now ask a question. A friend has a house of 750 square feet. How much can they be expected to get is the question. All right. So suppose if you capture the pattern of the data using a straight line, using this straight line model for 750 square feet, that means it would be around here. It would be around $150,000. $150,000, right? So suppose if I employ some higher order polynomial curve to capture the pattern of the data for 750 square feet, it would be around some $200,000. All right, that means the prediction depends on the model. All right, and the model that you employ depends on the assumptions that you make about the data. The model that you employ depends on the assumptions that you make about the data. That means whether you are assuming data to be linear or non-linear. If you assume the data to be linear, then you may try to employ, or you may take representation of the hypothesis as line or a hyperplane like this. And if you assume the data is non-linear, then you may try to capture the pattern of the data using some non-linear functions like something like second order polynomial curve, a third order polynomial curve, and so forth. So let us start with simple models, linear models, then we'll proceed to the non-linear models if time permits. The main idea of this lecture is to demonstrate you the concept of learning rather than talking about so many models. All right. So let me demonstrate the concept of learning, which is core part of all the machine learning algorithms and is so important if you want to learn machine learning. Right. So let us start with linear regression model. Linear regression model, it assumes that the data is linear. That means it is assuming that there exists a linear relation between output and the input variables. In simple words, it is estimating the output as a linear combination of the input variables. And for the simple words, it is trying to fit a line or a hyperplane to the data. So I hope I'm not going too fast in the process of covering many topics in 1.5 hours. Am I going too fast? Should I adjust the speed?
No, sir.
All right, cool. Right. So please interrupt me at any point of time if you couldn't follow something and if you have any questions. Any questions so far? Are you with me? Are you with me so far?
Yes, sir.
Yes, sir.
All right.
Yes, sir.
All right. That's great. Thank you. Thank you so much for your responses. All right. Let us begin with the linear regression model. So in the linear regression model, we are assuming that the data is linear. That means output is a linear combination of the input variables. That's what we are assuming. In simple words, we're trying to fit a line or a hyperplane to the data. All right. So if you remember our recipe, we have given a training set. The training set is passed to the learning algorithm. The learning algorithm is giving you the hypothesis, and you're making use of this hypothesis to make a prediction for the future instances. Now the question is, what is the representation of the hypothesis? The representation of the hypothesis depends on the model and the assumptions that you make about the data. So in case of the linear regression model, as I have mentioned to you already, we're trying to fit a line or a hyperplane to the data. Line when you have only one input variable, hyperplane when you have more than one input variable. So let us start with one input variable and try to fit a line. That means the representation of the hypothesis here is a line. So you know, right? What is the equation of a line? What is the equation of a line? Y equal to mx
Y is
plus
equal
b.
to mx plus c.
Yeah, so that's great, right? Mx plus b is the equation of a line. So if you see the representation of the hypothesis here, it's like a line, theta naught plus theta 1x, where theta naught is b, theta 1 is m, slope, right? So that means you're trying to fit a line. That when you have only one input variable, we call the model as univariate linear regression. If you have more than one input variable, we call it as a multivariate linear regression. So let us first discuss univariate, then we'll go to the multivariate. All right. So the representation of the hypothesis is this one. This is a line equation where theta naught and theta 1 are parameters of a line. All right. All good so far. You want to fit a line to the data. But which line? The many lines that are going through the data. You see this? The many lines. This line is going through the data. This line, this line, this line, this line. There are many, many lines. All of them are going through the given data. So which line is the best? Out of all these possible lines, which is the best line is the question. I forget about this problem for a while. Let me tell you an interesting problem. Let's suppose you're an engineer, civil engineer. You're asked to lay a common pipeline to the set of houses arranged something like this. So which direction would you choose to lay a common pipeline so that you can give a water connection to these individual houses? I give you options. One is this one and other direction is this. Which direction would you choose to lay a common pipeline out of these two options? What's your choice to lay a common pipeline? Hello?
Number 1, sir.
Number 1? All right. Anybody choose 2 or everybody 1? Not many responses this time. Feeling hungry? All right. I'll leave you early. All right. So please do respond. It's 1, right? Right. So why did we choose 1 over 2?
1, sir.
Yeah. Thank you. Thank you so much. Why did we choose 1 over 2? Is because the distance from the common pipeline to the individual houses is less in case of option 1 as compared to the option 2. Isn't that the reason for you to select 1? That's the reason, right? That means you want to optimize the cost. All right. The similar thing you want to do here also, right? Let's suppose this is the data given to you and you're asked to capture a pattern so that you can make a right prediction which is close to the underlying values, right? So let's see which line would capture the more important pattern of the data according to you. All right, I give you options here also. Line 1 or line 2. Which one is capturing more important pattern of the data? Line 1 or line 2? Line 1 or line 2? Which one is capturing more important pattern of the data? Or which one you think is a better line to capture the pattern?
Line 1.
Line 1.
Line 1, sir.
Line 1 is because the
L1.
line 1, yeah, the line 1, the difference between predicted value and the actual value is less, isn't it, as compared to the line 2? Isn't that the reason for you to select line 1 or line 2?
Yes.
Right?
Yes.
That means, can I say the line that minimizes the difference between the actual and the estimated prices is the best line out of all these possible lines? Can I say that?
Yes, sir. Yes, sir.
Yes.
I can definitely say that, right? Yeah. So the line that minimizes the difference between actual and predicted values is the best line out of all the possible lines. All right. So if that is the case, so what is making one line different from the other line? Let's take blue lines, 2x plus 3 and some 4x plus 5. What is making this line different from this line? The two parameters theta naught and theta 1, right? If theta naught and theta 1 are different, then the lines are different. Am I right? Right? That means when you're saying that you want to choose the best line, it means that you're saying that you want to choose the best parameters theta naught and theta 1. Isn't so? Isn't it so? Hello? When you're saying you want to select the best line, isn't that means that you want to choose the best parameters theta naught and theta 1? Am I right? Because the line is determined by these two parameters theta naught and theta 1. Am I right?
Yes,
Hello,
sir.
everyone? You right? So that
Yes, sir.
means
Yes.
your problem is boiling down to this. Your objective is this. Objective is to choose the parameters theta naught and theta 1 so that the predicted value h theta of x as close as possible to the original value y. Alright, that means you want to minimize the difference between predicted value h of x and the actual value y for all the training examples given in the training data. Alright, so let us try to formulate this mathematically. Alright, so this is our objective. The objective is to choose theta naught and theta 1 so that the cost is minimized. What is the cost? The squared difference between predicted value and the actual value for all the training examples are equal to 1 to m. And this 1 by m is to take the average, and this 1 by 2 is to simplify some future mathematics, and which is not affecting our objective. So the objective is formulated as follows. Your objective is to choose theta naught and theta 1 so that the squared difference between actual and predicted values is minimized for all the training examples given in the training data. Is the objective clear to everybody? Is that clear? So the objective is to choose theta naught and theta 1 or select theta naught and theta 1 in such a way that you minimize the squared loss, the squared difference between actual and predicted values. I hope that's clear.
Clear, sir.
Yeah, there is a lot of
Yes, sir.
theoretical notion behind the squared loss, but that's not possible to cover this within 1.5 time framework. So I'll not bother you about that, the theoretical background of the squared loss. But tell me one thing, how can I choose theta naught and theta 1 in such a way that the squared loss is minimized? How can I do that? How can I select a particular value, theta naught and theta 1, in such a way that I minimize this squared loss? All right. Can we do some magic? Say abracadabra, and select theta naught and theta 1 and say that, oh, see, this is the best theta naught and theta 1 I've got. Would you agree with me if I say it so? Definitely wouldn't, right? It's because you know that
sir.
the randomly chosen, the randomly chosen theta naught and theta 1 cannot be the best theta naught and theta 1. All right. If the randomly chosen theta naught and theta 1 cannot be the best theta naught and theta 1, what would be the best theta naught and theta 1 is the question. That's where exactly the gradient descent algorithm helps us to learn the optimal parameters of a model. So that means this gradient descent algorithm is an optimization algorithm which helps us to learn optimal theta naught and optimal theta 1 in this case. All right. So before we talk about the gradient descent algorithm, let us try to understand what is gradient. Let us try to understand what is gradient. So you knew about this, but let me just revise it. To demonstrate the concept of gradient, I've taken a simple example, that is a line equation, y equal to mx plus b. All right, let us try to understand the different terms in this equation or function. So here, x gives the information that how far it is along, y gives the information that how far it is up, and b is the value of y when x equivalent to 0. M gives the information that how steep the line is, which is nothing but the slope or the gradient. So this gives the information that how steep the line is. When M is positive, the line will be ascent like this. When M is negative, the line will be descent like this. When M equal to 0, the line will be flat like this. Okay, so suppose if I want to understand how a particular function is varying with respect to a particular variable, this slope gives you that information. So suppose if I want to understand how y is varying as I vary x, all right, m gives that information. All right, so if you want to understand the slope or the gradient of a particular function y with respect to a particular variable x, take the derivative of that function with respect to x. To be more precise and general, I just take partial derivative of y with respect to x, because sometimes in a function you have more than one variable. All right, so take the partial derivative with respect to each and every variable, and vector of all such partial derivatives will give you the gradient. So here I'm taking the partial derivative of y with respect to x. All right, to understand how y is varying as I vary x. So y means mx plus b. All right, so substitute that partial derivative of mx plus b with respect to x. So this is equivalent to m, which is nothing but the slope or the gradient. So to be more precise, if you want to compute gradient of a particular function with respect to a particular variable, take the partial derivative of that function with respect to that variable. So what should we do if I want to get the gradient of a particular function with respect to a particular variable? I should take the partial derivative of that function with respect to that variable, isn't it? All right, take the partial derivative of that function with respect to that variable. So can you confirm what should I do if I have to take the the gradient of a particular function with respect to a particular variable? How do I compute the gradient? How should we compute the gradient?
Partial derivatives.
By taking the partial
By means
derivative.
of partial derivatives.
Yeah, thank you. All right, keep this in mind because this is required for the next slide. Give me a second. All right. All right, this is the same thing. I'm skipping it. All right, so now let's get back to our problem. What is our problem? Our problem is to choose theta naught and theta 1 in such a way that the cost j of theta is minimized. All right, if I plot one of the parameter theta 1 versus the cost j of theta, it looks something like this. So in this, our objective is to choose optimal theta 1, which is corresponding to the minimum value of j of theta. That means I'm looking for this one. This is my optimal theta, isn't it? But when I randomly initialize theta, it can be anywhere. It can be here, it can be here, it can be here, it can be anywhere, because I'm just randomly initializing it. So from that point, how can I go to the optimal point is the question. All right, so let me tell me one thing. So suppose when I randomly initialized, my theta 1 is somewhere here. So can you tell me the slope of the function at this point? Is it a negative slope or is it a positive slope? Is it descending or ascending? How is it at this point? What is the slope?
Negative slope.
It's a negative slope, right?
Descending.
Because descending, right? Descending means negative, right? It's negative, right? That's good. So right now you're here and you want to go here, right? Your current theta is here and you want to go to here. All right. So imagine that you are somewhere here at this place and you want to go here. This is your destination and this is your source. So which direction you should move to reach to the destination? Forward direction or backward direction? Which direction we should move to reach to the destination? In this case, you're here and you want to go here. This is your current theta and this is the optimal theta. So which direction should we proceed to reach to the
Right to
optimal?
left. Right to left.
Right to left means this direction.
From my side, it's a left to right.
It's left to
Sir.
right, right? Right, left to right, isn't it? So left to right, that means forward direction, isn't it? That means, should we increase theta or should we decrease theta if I want to reach to the optimal value?
Decrease the theta.
Decrease theta, as we move this way, it is increasing, right? The theta is 0 here, maybe. As we move this towards this, it is increasing, isn't it? Generally.
Oh, my negatively it is increasing, sir.
What do you
Or
mean by that? No. See, don't get confused. Suppose, let's take different values of theta. 0, some 10, 1, 2, 3. I'm just taking some random values.
Okay, sir.
Okay. So right now you are here, and this is the optimal point. Okay.
Which one, sir?
So
1.
that means
Irukku.
this is your current, which is 1, and optimally some 2.1. Okay. So to reach to the 2.1, should I increase theta or should I decrease theta? It means
Increase.
increase only, right? Right.
Increase by 1.1.
Yeah, but it should be increased, right? We don't know what is the correct value when you're here, but you should increase. That means you should move in the forward direction. That much we are sure, right?
Okay, sir.
Isn't it? Right.
Yes.
So suppose when you randomly initialize it, let's suppose theta is somewhere here. It means this is your current theta. Can you tell me what is the slope at this point? Is it ascending, descending, positive or negative?
Positive, ascending.
Positive, right? So this is positive. So right now you are here and you want to go here. Should I decrease or increase? Suppose if you are here and you want to go here. Okay. Should I increase or decrease? Decrease, right?
Decrease.
Right. That's great. That means, do you agree with me that when the slope is negative, we should increase theta to reach to the minimum point? And
Yes, sir.
when the slope is positive, we should decrease theta to reach to the minimum point.
Yes, sir.
Right. That means we should move in the opposite direction of the gradient. When negative, increase. When positive, decrease. All right. So
Yes,
is this okay if I do this? Okay, I'll come back to this. Is this okay if I do this? I initialize theta naught and theta 1 to some random values. And I repeat the following process until convergence. Theta j equal to theta j minus alpha times the derivative of j with respect to theta j. All right. So this is what I'm doing. Let's try to understand this. Can you tell me, ignore alpha for a while, take that to be 1, ignore it. But tell me this, what this gives you, derivative of j with respect to theta j? I told you in the previous slide. If you want to compute this gives you the gradient, right? Or the slope, that's what we
Partial
talked about.
derivative.
Right? The partial derivative of this gives you the gradient or the slope. That's what I told, right? So that means the partial derivative of j with respect to theta j gives you the slope or the gradient. So what are we supposed to do if the slope is positive? Decrease or increase?
Decrease.
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 Right? Decrease. So suppose if this is positive, see what is happening. Theta j equal to theta j minus some positive value. It means you're subtracting some positive value from the existing and updating it. That means you're decreasing it, right? Suppose let this be some 1. That means theta j equal to theta j minus 1. means you're decreasing it, isn't it? Hello?
Yes, sir.
Am I right? You're decreasing it, right? So
Hmm.
let's suppose this is a negative value. What am I supposed to do if it is a negative value?
Increase.
Increase. Okay, let us
Increment.
take this to be, yeah, increase. Let us take
Minus
this to
of
be
minus
-1.
positive.
Yeah, -1. So minus of minus, it would be positive. That means theta j
Positive.
equal to theta j, yeah, plus some positive value. You're
Yes.
increasing it, right? So that means this algorithm is doing whatever that you want. When the slope is positive, you want it to decrease, and it is doing that. When the slope is negative, you want to increase, and it is doing that, right? So this algorithm is called gradient descent algorithm. This algorithm is called gradient descent algorithm. So I hope the gradient descent algorithm intuition is clear to everybody. Is that
Clear,
clear?
sir.
All
Clear.
right. All right. All right.
Yes,
So
sir.
now, yeah, that's great. Thanks so much. So let's go back and see this. So what if you have more than one input variable? If you have more than one input variable, that can be visualized. This can be visualized like a ball in the multidimensional space like this. And our objective is to reach to the bottom of this ball, which is like in the valley point of this ball. That means in that case, you'll be initializing the theta naught and theta 1, both of them to some random values, and gradually adjust both of them so that you reach to the minimum point. So if you see this ball from the top view, what do you see? You see concentric circles like this, right? And our goal is to reach to the center point of these concentric circles. All right. So anywhere on one circle, the cost is same. So it's like this. This is one circle, and at a different height you have another circle. At different height you have another circle like that. Right. So our objective is to reach to the center like this. You got it right?
Yes, sir.
Yeah. All right. So this is what you get when you take the derivative of the cost function with respect to theta naught. You can try this at home. This is what you get when you take the derivative of j with respect to theta 1. You just have to substitute them in this formula and do it. Now coming back to this, there is one term that we have ignored here, which is alpha. So what is this alpha? This alpha is also called learning rate, and this is called learning rate, which is also called as step size. Learning rate, more formally, but more commonly it is called step size. Learning rate or the step size. What is it? Okay, so this decides how much I should increase or decrease theta. All right, if alpha value is big, you'll be taking bigger steps. If alpha value is small, you'll be taking smaller steps. So imagine it this way. Suppose you are in some beautiful location where there are a lot of hills. And let's suppose there are two beautiful hills. In between that, there is a valley point. And in this valley point, you have got a beautiful home. And imagine that you're somewhere here on one of the hill and you want to go to your home. Okay. So imagine you're a big Rakshasa like Kumbhakarna. Okay. Very giant personality. Okay. So what happens if I take one step from here? One step from here, what will happen? Because you've got a very lengthy leg, with one step you'll be going here. Right? Okay.
Yes,
Now
sir.
you realize that, oh no, I have already crossed my home. I should go back. Okay. Again, you're taking one step back. With one step back, you're reaching to this. One step forward, you're coming here. One step backward, you're going here. One step forward, you'll be going here. Will you be able to
I
go to
am
your
not
home?
reaching my house at
You're
all.
not reaching your house. Right. That's right. Right. It's because you're moving front and back between the hills.
Roaming. Sir.
Yeah. You're moving front and back between the hills, but never be able to reach your home. All right. Even if you're able to go to your home, your path to reach to your home is zigzag. Right? It's because you're
Yes, sir.
taking front and back steps. All right. So
Excellent, sir.
imagine you're a tiny ant. Okay. You got a tiny legs. Okay. That means you're walking like tan like this. Very small steps. Will you be able to go to your home?
Long time.
It takes
Largest.
very long time to go to your home, right? It means,
Yes,
so
sir.
this alpha is something like that. All right. If alpha is
Excellent
so
example,
small,
sir.
if alpha is so small, it's like an ant. It takes two too long to converge to the optimal point. If alpha is too big, that is also problematic. Why? Because if alpha is too big, you're taking bigger steps. In that process, you may cross the optimal point and reach to the other end. That means your cost is increasing, not decreasing, just because you cross the optimal point, because of the big step that you have taken. All right. So you have to fix alpha in such a way that it shouldn't take too long time to converge. At the same time, it shouldn't cross the optimal point also. All right. This alpha is a hyperparameter of the model. So you have to tune the hyperparameter and choose the optimal value for alpha, where it is, the minimizing the cost at the same time converging fastly. All right. I hope you understood the concept of alpha and the step size, its importance in the updation rule.
Yes,
Is
sir.
it clear to everybody?
Clear.
Yeah.
Clear,
Cool.
sir.
That's great. See, this is an example. You see that as the line is, capturing the pattern of the data, the cost is decreasing, as you can see. Initially, the line was like this. The cost is so high. All right. As the cost is getting close to the examples, you can notice that the cost is decreasing. So the error value, you notice, when the line is away from the points, the error is very high. When the line is close to them, the error is decreasing. That means you'll be gradually adjusting this line in such a way that the error is minimized, the squared loss is minimized. And the corresponding cost also in terms of this convex where that is lying also can be seen. Initially, it is at some high value of the error. Gradually, it is reaching to the minimal point. In the bowl, it is a minimal point. This is the minimal point, right? All right. Thus, whatever that we have discussed so far is a gradient descent algorithm, which is one of the optimization algorithm. There are many other optimization algorithm, but with small variation, there are two more, which are stochastic gradient descent and mini batch gradient descent. All right. The algorithm that we have discussed now, the gradient descent algorithm, we also call it as a batch gradient descent algorithm. Batch gradient descent algorithm. Both of them are same, in which to make to compute the gradient of a cost function with respect to a particular parameter, we compute the gradient with respect to each and every example and finally take the aggregate as our final gradient. That means the gradient is computed with respect to example 1, example 2, and so on, example m, and take the average or aggregate of all of this. So that's what is done here in ways of the gradient descent algorithm. If you notice the formulas also, you see that the gradient is computed with respect to all the examples equal to 1 to m. All right, this is gradient descent algorithm. The advantage of it is that because you're computing the gradient with respect to each and every example, it is stable because there are many examples you have considered and considered the aggregate of all of them. So it's stably decreasing like this. All right. On the other hand, in case of the stochastic gradient descent algorithm, we only compute the gradient with respect to one example at a time. That means the gradient is computed with respect to example 1 and update according to that. And next time you compute the gradient with respect to 2, 3, so on, m. That means at a time one example, but you're repeating over all the examples. All right. At a time one example, repeating over all the examples. The advantage of this is that the updations are so frequent. It means you need not have to wait for a longer time to make the updations, unlike in case of the gradient descent algorithm. But the disadvantage is that because you're considering only one example at a time, it is so unstable. All right, it's maybe moving front and back like this. It's unstably decreasing like this. All right. So the advantage is that stable here, but the disadvantage is that it takes longer time to make an updation, because let's suppose in the case where we have 10 million number of examples in the data set. That means you have to compute gradient with respect to 10 million examples and take the aggregate and update. That means to make a single updation, you have to compute the gradient with respect to 10 million examples, all right, which is longer time to make an updation. All right. But on the other hand, in case of the stochastic gradient descent algorithm, it is making frequent updations, but the disadvantage is not stable. All right. To take an advantage of both and overcome the disadvantages of both, we have something called mini batch gradient descent algorithm. So in this, you're considering all the example to make a prediction, to make an updation. Here only one example. What is something in between? Take the subset of the example. That means given a data, divide them into small batches. All right. That means suppose if I have 1 lakh instances, I can divide them a batch of 100 like that 1000 batches, or batch of 1000 like that 100 batches. All right. So and compute the gradient with respect to each batch. All right. And repeat over all the batches. So that means here you're considering the gradient with respect to one batch of examples. It's not just single one. So 100 or 1000, anything like that. That means you're considering sufficiently good number of examples and taking the average. That's why it is stable. And because you're considering only the subset, which is a small subset of the entire data set, so it doesn't take too long time to make an updation, right? That means it is overcoming the disadvantages of both and taking the advantage of both. So this is a batch gradient descent algorithm in which you have to wait for a longer time. All right, initially it may be some fluctuations, but gradually stably it is decreasing, as you can see, over a period. This is stochastic, so it's like that going front and back, because you're considering only one example at a time. All right, and this is mini batch, which is in between both. Okay, which is somewhat stable, somewhat somewhat fast also. All right, like this. All right, which is balancing both the previous ones. I hope you understood the difference between batch, stochastic, and mini batch. Is that clear to everyone?
Yes, sir. Yes.
Yeah. Half an hour more. All right. Then multivariate linear regression. In the case of multivariate linear regression, we have more than one input variable. All right. Earlier, so far, we have considered only one input variable. Okay. So if you have more than one input variable, we call it as a multivariate linear regression. So let's take the same example of house price prediction. Not just the size of the house that influences the price, right? There are many other factors which influences the price, like number of bedrooms, number of floors, age of the home, etc. So that means considering more number of example can lead to more accurate prediction. All right. So here the number of input variables are 4, which is more than 1. So we call it as a multivariate linear regression. So if I denote the number of features as n, okay, and m is the number of examples, we generally use the superscripts to denote the instance number, and subscript to denote the feature number. For example, x superscript 3 referring to the instance 3, which means this example 3. And x superscript 3 subscript 2 means the second feature of the third house, which is this one. Right? The subscript is the feature number and the superscript is the instance number. So in case of any variate linear regression, the representation of the hypothesis is a line, theta naught plus theta 1x. If you have multiple features, it's a hyperplane. Theta naught plus theta 1 x1, theta 2 x2, so on, theta 4 x4. In this case, if there are n features, then it would be theta naught plus theta 1 x1, theta 2 x2, and so on, theta n xn. So if I want to generalize this, let's take x naught equal to 1 and rewrite the equation theta naught x naught plus theta 1 x1, so on, theta n xn. This is the representation. Can you tell me how many parameters you're supposed to learn in this model? If you have n features, how many parameters are you learning here when number of features are equal to 1? You're learning 2 parameters, right? Theta naught and theta 1. Right. How many parameters you're supposed to learn here? Theta naught, theta 1, so on, theta n.
5.
Right? How many? N plus 1.
5 parameters.
N plus 1 number of parameters. Here also the same. Cost function is the same. Only thing is that the representation of the hypothesis is now a hyperplane. And this updation rule is also same. Earlier we were updating 2 parameters, j equal to 0, j equal to 1. And now we are updating n plus 1 number of parameters, 0 to n. This is the updation rule. All right, that's about the gradient descent in both univariate and multivariate linear regressions. All right, when you're practically implementing this gradient descent algorithm, there are certain things that you need to take care of. There are certain things that you need to take care of. So one such thing is feature scaling. One such thing is feature scaling. All right, so what is feature scaling and why is this important? Right? Let us have a look at this. So if you look at this example, the first feature was size of the house, which is generally in the range of 800 to 3000 square feet. The second feature is the number of bedrooms, which is generally in the range of 1 to 5. Do you agree with me that there is a lot of range differences between these two features? One is in thousands, the other one is just numbers. So do you agree that there is a lot of difference, range difference between them? Hello? Do you agree that there is a lot of range difference between these two features, size and the number of bedrooms? All right, I think it's the time for your dinner. All right, let me wind it up in 15 minutes. All right, give me some time. All right, please do attentive for at least 15 minutes. We'll wind up. Right, so the first feature is the size of the house in square feet. The second one is the number of bedrooms. There is huge range difference between these two features. So what happens if there is a huge range difference between the features? If there is a huge range difference between the features, your contour graph will become thin and tall like this. So earlier, if you have seen the contour graph, it was like concentric circles, not concentric bubbles. But if there is a huge range difference, it will become thin and tall like this. As a result, when you're making an updation, you see that when you're making an updation of theta 1 minus alpha times something, in this something you see this, h theta of x, which includes theta 1, theta naught plus theta 1 x1, theta 2 x2, and so on. So that means even if you're making theta 1, you also have theta naught in it. You also have theta 2 in it, right? Because in this part you have this, right? Right. It's because suppose this value that you are considering is very big and this one is very small. That means other features are very high and this particular one is low. And what happens because of this range differences, when you are subtracting, because this part is so big and this is so small, when you are making an updation, you may be increasing it or decreasing it more than required. As a result, what happens, right? When you are making these updations with a huge range differences, you may be increasing theta or decreasing theta more than required. So that means you're here, starting here, you're increasing it. You're increasing it. When you're increasing it, you're crossing the optimal point. It is increasing. Now you realize that, oh no, I have already crossed my optimal point. I should go back. You're decreasing it. When you're decreasing it also, because of the range differences, you're decreasing it more than required. That means you're increasing, decreasing more than required. Increasing, decreasing more than required. As a result, your path to reach to the optimal point is becoming zigzag like this. Okay. So suppose given two choices. Okay. One is zigzag path, the other one is a straight path. Which one would you prefer? Straight path or zigzag path? Obviously the straight path, right? Because you'll go fast, isn't it? So, but then if you don't apply feature scaling, if the features are in a different scale, different range, then you will end up with a zigzag path. To overcome that, we have something called feature scaling, which is basically bringing the features into the similar range. Okay. Suppose here the size, which is x1. Second one is the number of bedrooms. Let's suppose you have 800, some thousand, 12,000, 1200, etc. as your data. Right. Similarly, x2, you have 1, some 2, 3, etc. as your data. To bring them into the similar range, one simple thing that I can do is that take the maximum. Let's suppose 1200 is the maximum. Divide everything by 1200, which will bring them in the range of 0 to 1. Similarly, suppose 3 is the highest. Divide everything by 3, which will bring them in the range of 0 to 1. Right? So that means you're bringing the features into the same scale. That is called feature scaling. Just simple approach that I have demonstrated here, but there are many choices for the feature scaling. So these are some of the popular feature scaling technique, max, min, mean normalization, Z-scale. So what happens is that when you apply feature scaling, your contour graph will become like this, concentric circles, and your path to reach to the optimal point is almost like a straight line. So if you don't do it, your path to reach to the optimal point is becoming like this, and it is not guaranteed that you reach to the optimal. That's about the feature scaling. So the second thing that you need to take care is learning rate alpha. Okay. As I have mentioned to you already, the learning rate alpha is a hyperparameter. You should choose optimally. It shouldn't be too small. It shouldn't be too big. All right. You should ensure that it is working for your objective. Our objective is to minimize the cost. Suppose if the cost is increasing, that means your alpha is not right. Okay. Because suppose it is increasing, probably you need to choose a smaller value for alpha. Why? When the cost will increase, when you cross the optimal point, only the cost will increase, right? When you will cross it, when you take a big step, right? That means you need to decrease alpha when the cost is increasing. Suppose if it is decreasing like this, or the number of iterations, then it is working. All right, it's working for your objective. All right, I think I will wind up here because I see that a lot of people. I mean, if you're interested, let me know. I can continue. Otherwise, we can wind up here. I can take questions if any for next 10 minutes and wind up. Any questions? Any questions from everyone? Anybody? All right. Sir, shall we? What do you think? Like, should we continue or?
Yes, sir, you can continue.
Okay. All right. That's great. I'll skip this part. All right. Let me talk about polynomial regression and then wind up. So far, we assume that the data is linear, right? It means you're employing a linear regression model to capture the linear relation between the output and the input variables. What if the data is non-linear? That means, what if there does not exist a linear relation between output and the input variables? Then we go for some non-linear hypothesis, which is polynomial regression. All right. So here, we're trying to capture the nonlinear relation between output and the input variables. Let us start with an example here also again, but different, same example, but different features. So let's suppose I have two features. One is the frontage, the other one is the depth. So frontage is the width of the plot alongside the route. Depth is the depth away from the route. So given these two features, I need not have to restrict to these two features. Instead, I can create new features. Like, for example, I can multiply the frontage and the depth, get an area of the plot. I can use the area to make a prediction. An area is a better indicator than the frontage or the depth, right? Often, by creating new features, you may get a better model. So if I look at this world example of the house price prediction, earlier we were trying to fit a line in which the representation of the hypothesis is theta naught plus theta 1x. So if I go for the second order polynomial curve, it is theta naught plus theta 1x plus theta 2x squared. For third order, it is theta naught plus theta 1x plus theta 2x squared plus theta 3x to the power 3. Look at all these three models: line, second order polynomial, which is indicated with the blue curve, and third order polynomial, which is indicated with the green curve. And tell me which one you think capturing the pattern well: line or second order or third order?
Third.
Third, right? Third order is better, right? So the representation of the hypothesis, if you see, theta naught plus theta 1x, theta 2x squared plus theta 3x to the power 3. So here, x is the original feature that you have given, and using which you're generating x squared, using which you're also generating x to the power 3. So if I imagine this x as my feature 1, x squared as feature 2, x cubed as feature 3, and rewrite this equation, theta naught plus theta 1 x1, theta 2 x2, theta 3 x3. How is this looking like? Isn't it a multivariate linear regression? The same as multivariate linear regression, right? That means you're not changing the solution, you're only changing the data. Means you're transforming the problem to some high dimensional space where there exists a linear relation and then applying linear regression. So the polynomial regression is just generating polynomial features and then applying linear regression model to it. That's all. All right. Okay. So to see the effect of this, the polynomial, I have an example here. This is the general representation of the hypothesis theta naught plus theta 1x, theta x squared plus theta mx to the power m, when only one input variable is there. All right. So for different values of m, you have different models. When m equal to 0, your hypothesis h theta of x is just theta naught. When m equal to 1, it is theta naught plus theta 1x. When m equal to 2, it is theta naught plus theta 1x plus theta x squared, and so forth. So for different values of m, you have different models. And for a given m, what theta should we choose is determined through the parameter selection. So here is an example, the synthetic data example. You have two dimensions, x and t is the target, or y. We can. So x is generated randomly between 0 and 1, and y is generated using sine 2 pi x. And add a bit of noise to it to spread the data. All right. So that means suppose x is generated randomly, 0.1. So give y as a sine 2 pi x, sine 2 pi times 0.1, and add a bit of noise. You'll get corresponding y. This is the corresponding y. So if you look at the figure, the green curve is the underlying model from which we have generated this data, and blue points are the data points that we have generated. Blue points are the data points that we have generated, which are around the curve because we added a bit of noise, not exactly on the curve. All right. Now the task is to learn a model which is close to this underlying model. If you can learn a model which is close to this green curve, then you're successful because that's the pattern. Right. Let's see the effect of m, or the degree of the polynomial in this case. So when m equal to 0, the representation of the hypothesis is just theta naught, and this is what the model that I've got. All right. So what do you think about this? Is it close to the underlying model? Is it capturing the pattern of the data? What is your opinion about this? What's your opinion about this? Is this red curve close to the underlying model, which is expressed as a green curve?
No, sir.
No, right? No,
Green.
right?
No.
Not at all.
No.
Not at all close. Yeah, that's good. All right. So what about this? When m equal to 1, you got this. Is it better than the previous? Is it
Yes,
better
sir.
than the previous?
Yes.
Better.
Yes.
But is
Yeah,
it close
it's
to the
better than-
underlying
Yes, sir.
model?
Yes, sir. Yes, sir.
Is it close to the
No,
underlying
sir.
model? Not at, right?
Not
Right.
that.
No, sir. No, sir.
Not that.
So when m equal to 3, this is the representation. What do you think about it? Is it better than the previous two?
Yes, sir.
Yes, sir.
And is it
Close,
close?
sir. Little bit close.
It's
Little bit
close
closer.
also.
Yes.
Right. So what is that you have noticed from m equal to 0 to m equal to 3? When m equal to 0, the model is so simple, but restrictions are very high. So when m equal to 0, it's just theta naught. It means it should be an axis parallel line. It is independent of x, right? Among all the possible axis parallel lines, you may be choosing the best axis parallel line, which is this. But that best axis parallel line is not capturing the pattern, right? So the model is simple, but the restriction that it is imposing is very high. It's not flexible, right? You're relaxing it a bit when you increase the complexity of the model to 1. Now you're saying that it can be any line, need not be an axis parallel line. So among all the possible lines, you may be choosing the best line, but that itself is not able to capture the pattern. Although you have increased the flexibility a bit, it reduces the error, but it is not able to capture the pattern. When m equal to 3, you're saying that it need not be a line, it can be any curve. Okay, so it is capturing the pattern. All right, that means the model's complexity is increasing. That means model is getting more flexibility to capture more complex patterns in the given data. Agree? Hello, everybody, agree to this? As the model's complexity is increasing, model is getting more flexible to capture complex patterns in the given data. Right. If that is the case, let us take m equal to 9. And this is the model. What do you feel about this?
This does not fit. The
Why not?
third order is better.
But you see this, it is making right prediction for all the training examples. Perfect prediction. You see that it is going through
Yes,
each and every data point. So why did you say
Yes,
it is
sir.
not better? It's a zero error, isn't it?
But it does not. Does it fit the pattern exactly?
That's what exactly. Like, though it is making a right prediction for all the training examples, it is not able to capture the pattern. That means, given any new instance which is coming from the same distribution, it will fail. Okay, that means suppose if I generate another data by following the same process, it may be here. This is the actual and this is the predicted. The difference is so high, right? So this situation is called overfitting. Overfitting is a scenario where the model performs very well on the training data, but poorly on the test data or new instances. So we call this as overfitting problem. We call this as overfitting problem. Got it right? What is overfitting? Right.
Yes, sir.
So if you see the different values of m, when m equal to 0, it is underfitting. Both the training and testing errors are high. As you increase the degree of the polynomial, it's gradually decreasing, but at this point when m equal to 9, the training error is 0, but the test error is so high. The difference is so high. So this is called overfitting case. This is underfitting, this is overfitting case. So how to avoid this overfitting? So one of the solutions to avoid overfitting is increase the size of the data. Increase the size of the data. So now you see, now I increase the number of data points to 15 from 10. Here it is 10. I've increased it to 15. Now you see the difference. Here curve was oscillating too much, but the oscillation is reduced a bit here. It's not having that much variance now. Agree? That's the case. Let's increase it to 100 data points. Same ninth order polynomial. No change in the data, no change in the model. Only increase the number of data points to 100. Now you see, it's almost perfect, right? So increasing the size of the data set elevates the overfitting problem. All right, but tell me one thing. Is it possible to increase the size of the data always?
Maybe not always.
Not possible.
It is not
Because
possible in all cases.
this is synthetic data. We know the underlying model. We can generate as many number of data points as we want. But what about the real-time data sets? Is it possible? Do you know the underlying model? You don't know, right? Through the techniques like sampling, you can generate few data points, but you cannot generate as many number of data points as you wish. That's not possible, right? That means increasing the size of the data cannot be the generalized solution to increase the overfitting, to avoid the overfitting problem. Okay, so if that is not the generalized solution, what is the generalized solution? So to come up with a generalized solution to any problem, you need to understand the root cause of that problem. So what is the root cause? Let us analyze by understanding the parameters. So here W0 to W9 are theta naught to theta 9 in our notation. Don't get confused. So when m equal to 0, you have only one parameter theta naught, which is in the smaller range. When m equal to 1, you are learning two parameters. They are also in small range. When m equal to 3, you are learning four parameters. They are in a relatively moderate range. Excuse me. When m equal to 9, you're learning 10 parameters, and so you see the parameters range. They are varying from minus 10,61,800 to plus 10,42,400. Okay, so you see that, do you notice that they have grown really big? They're very big, they became very big numbers, isn't it? Hello? Notice it?
Yes, sir.
They've grown really big.
Yes, sir.
When do you say there is a variance in the data? If the spread is more or spread is less? Suppose I give you two data sets. One is this. One is this one. Which one has more variance, D1 or D2?
D2.
D2. When the spread is more, the variance is more, right? See that
Yes,
there are
sir.
nine feet parameters. They spread in the range of minus 10 million to plus 10 million. It means the spread is very high. That means the variance is very high, right? It's because of
Yes.
this
Yes, sir.
variance. Because of this variance, curve was oscillating too much in between the data points. It's because of that you're getting overfitting problem. So the root cause is that the parameters are grown really big. That means in a process of minimizing the error, the squared error, we're not concerned about anything else. We're only concerned about minimizing the squared loss. In that process, we do not have any restriction on the parameters growth. As a result, parameters have grown really big. It's because of that, a lot of variance is induced into the model. It's because of that curve was oscillating and you got overfitting problem. So this is the root cause. Can you come up with a solution? The root cause is that parameters are grown really big. It's because that's the root cause. So if I ask you to provide a solution to this, what is your solution for this?
Select the most appropriate parameter.
So you should restrict the parameters growth, right? You shouldn't allow them to grow too
Yes.
big, isn't it? That means in addition to minimizing the squared loss, now you also have got an additional objective, additional responsibility, which is minimizing these theta values, right? So that means in addition to minimizing the squared loss, this was the earlier one, you also want to minimize theta values. This is called regularization term, and lambda is the weightage that you're giving to the regularization term. L is the norm of the norm value. When L equal to 1, we call it as L1 norm. When L equal to 2, we call it as L2 norm, and so forth. All right. So the idea is to penalize high weights that contribute to high variance and sensitivity to the outliers. All right. When L equal to 1, we call it as a lasso regression. So L equal to 1, we try to minimize absolute value of theta 1 plus absolute value of theta 2 and so on absolute value of theta n. When L equal to 2, we try to minimize square root of theta 1 square, theta 2 square and so on theta n square. When L equal to p, we try to minimize pth root of theta 1 to the power p, theta 2 to the power p, and so on theta n to the power p. Okay, when L equal to 1, we try to minimize absolute values of thetas. It's like this. Earlier, according to this objective, our objective is to reach to the center point of the contour graph. Now you have got an additional objective, which is minimizing the theta values, according to which you want to go here. Okay, both of them are not same. This objective is pulling it towards this, and this objective is pulling it towards this. Okay, so imagine this is a wife and this is husband. Wife want 11-seater car. Husband can only afford 4-seater car. What's the solution? Look for the compromising point where both the objectives meet. 7-seater car, right? So this is the intersecting point where both the objectives meet, right? So this is the optimal point according to the new objective, according to which you may be compromising to a certain extent on minimizing the squared loss, but you're ensuring that your model is generalized to all the data, not just the training data. So this is the optimal point. Similarly, ridge regression. So the shape will vary based on this one. All right. Earlier it was like diamond, no? This is like cycle equation, more or like cycle equation. So this is also the same. According to the second part, you wanna go here. According to the first part, you wanna go here and look for the intersecting point where both the objectives meet. For different values, this is by the way called ridge regression. When L2 norm is employed, we call it as a ridge regression. If both are employed, L1 and L2 norm with appropriate weightages lambda 1 and lambda 2, we call it as elastic net regression, which is in between. For different values of L, you have different shapes, as you can see there. Now we see the effect of regularization. When lambda equal to e to the power 0, log lambda equal to 0 means lambda is e to the power 0, that means 1. That means you're giving very high importance to the regularization. So if your objective is like this, if you give so much importance to the regularization, it means you're more concerned about minimizing the theta values than, than minimizing the square loss. It means your objective is more inclined to this. That means your theta 1, theta 2, so on, theta n will go close to 0. If they go close to 0 in a function of theta naught plus theta 1 x1, theta 2 x2, so on, theta n xn, if they are all close to 0, this part is 0. That means your model is almost like theta naught. It means it is underfitting. That means if you give too much importance to the regularization, you see this. If you give too much importance to the second part, this part, your solution will be more inclined to this. As a result, your all theta values will go close to 0 and it underfits. If you give no importance to this, the solution will be more close to this. If this is 0, this will be inclined to this. That means you are overfitting. So you have to give appropriate weightage so that it correctly fits. So this is correct fitting. So lambda equal to 1, underfitting case, parameter values are almost like zeros. Lambda equal to 0, no importance to the regularization. They have grown really high and it's overfitting. This is appropriate weightage, earning values in the moderate range. This is the effect of regularization. So that means when you give too much importance, it underfits. If you give no importance, it overfits. So that's all. If you have any questions, I can take. Otherwise, that's all for today. I can take questions. Thank you and happy learning.
Yeah, participants, if you have any questions, you can post or you can ask.
I hope you understood the lecture.
Yes, sir. Yes, sir.
Very well explained, sir.
Thank you, sir.
Yes,
Thank
sir.
you so much.
Today's session was extremely useful and very engaging session. On behalf of the FDP team, we sincerely thank you, Dr. Venkateswara Rao Kagita, for your wonderful talk on supervised learning. You explained the mathematics of regression in a very simple and clear way. The examples you shared, even the numerous humorous ones, made complex concepts easy to understand. Many topics that we often find difficult or tend to skip were handled by you with clarity and depth. You answered our why and what questions, many childhood questions thoughtfully, making the session highly interactive and enjoyable. We truly benefited from your explanations and insights, sir. We look forward to invite you again with more time to cover the complete content. Thank you once again for your valuable
Small appeal,
contribution,
madam.
sir.
Small appeal, madam, from my side. Yesterday class is there, na? That PPT and video and that Google Drive link, if we share, it is somewhat
Yes, sir.
network
Yes, sir.
issues
All
will
the
be there,
material
na?
will be shared. All the material will be shared to you once the FDP is fully done. After Saturday,
Fully
that will
done,
be
madam.
shared.
In the national at last examination, not for the examination sake, for some covering side, it is better, na? You at least 2 days material submit, provide tomorrow. Another
Sure,
2
sir.
days
Sure.
material.
Sure. We'll get the PPT from sir and we'll share it with the
Video link,
WhatsApp
madam.
group.
This one 2 hours 90. Now it is not possible to send total in Google Gmail. So you give permission through Google Drive, madam.
Okay,
So
I'll
that
give you
only
access, sir, to
participants can
access that.
access.
Yeah, I'll provide you
Already I
access.
attended number of workshops like this, faculty development programs. They will do the same task. Whenever lengthy video session is there, they will share that link and give access to us. We can learn more information. Suppose internet breaks like this, if it is there.
Yeah, sure,
Okay.
sure. We'll share, sir. We'll share.
Thank you, madam.
Thank you, Kakita, sir, once again. Thank you for your valuable
Thank you so
contribution.
much. Good night, everybody.
Yeah, thank you, sir.
And feedback link?
Yeah, participants' feedback link is shared in the chat. The link will be active for next 15 minutes. And tomorrow we'll meet for session 5 at 6 p.m. Thank you once again and good night.
Sorry, there is a question.
Yeah.
Sorry. Was says D2 Priya. I think Priya. Yeah. Lesser regression is best suited for feature selection. Yes. The answer, straightforward answer is yes. Are you there, Priya?
Priya? Miss Priya.
All right. Maybe the recording she'll look at it later. It is suitable for lesser regression. Lesser regression suitable for the feature selection. Is because if you look at this, let me just give me a second, madam. I'll wind it up.
Yes, sir.
I'll
Yes, sir.
really-
No problem. You can explain.
Just a second. Okay. If you look at this lesser regression, if you look at the optimal point, you look at the value of the optimal parameters. So this is 0, right? W1 is 0 at the optimal point. So that means if I have a model something like this, W0, which is theta naught in our case, W1, X1, W2, X2, so on. Okay, if W1 is 0, are you giving any importance to this feature? 0 multiplied by X1. It means you're not considering X1 at all, right? That means it is automatically ignoring this feature, right? It means given a certain set of features, there may be some features which are irrelevant. This lesser model automatically ignores those features. Okay, that is why it is called embedded feature selection technique. Okay, suppose if I am collecting a student information, I may be collecting a lot of information when collecting, right? Maybe what is his name, what is his native place, what is his blood group, what is his height, weight, so many things. Okay, how many hours he attended. Do you think all these are relevant for the grade prediction? Maybe how many classes he attended may be relevant to the grade prediction, but not his blood group, not his height, not his weight. Means if you consider certain problem, there may be certain features which are irrelevant for the prediction task at hand. It automatically ignores them. That is why lesser regression is called embedded feature selection technique. Okay, which is also acting like an inbuilt feature selection technique. Thanks. I mean, I hope that answers the question.
Thank you, sir. Thank you.
All right, ma'am. Thank you. Good night, everybody.
Thank you. Good night, sir.
Thank you, sir.